Module 2, Lesson 1, Forces and Interaction. This presentation is an introduction to Module 2 on forces and the laws of motion. Specifically, this discussion will be all about an introduction on the properties of forces, common types of forces, and the superposition of forces. In the previous lessons, we have learned how to describe the motion of an object in 1 or 2 dimensions. But what are the underlying causes of motion? For example, how can a tugboat push a larger ship that's much heavier? Or why is it harder to control a car on wet ice than on dry concrete? In the preceding lessons, we learned the language of kinematics to describe motion. Now, we are ready to think about what makes a body move. In this module, we will expand our learning to the concept of force and mass. To begin with, we try to answer this question on what makes a body move. Well, we might answer immediately, force. In everyday language, a force is a push or a pull. Meanwhile, a better definition would be it is the interaction between two bodies or between a body and its environment. In summary, a force or forces are pulls or pushes. A force is an interaction between two objects or between an object and its environment, and technically, a force is a vector quantity. That's why we always refer to the force as that one that exerted by a body on a second body. As shown in the figure A, force is a vector quantity. That is, you can push or pull a body in different directions. When a force involves direct contact between two bodies, such as a pull or a push that you exert on an object with your hand, we call it a contact force. The figures in this slide show 3 common types of contact forces. The first one is the normal force. It is a force exerted on an object by any surface with which it comes in contact with. The adjective normal means that it always acts perpendicular to the surface of contact, no matter what the angle of the surface is. In contrast, friction is a force exerted on an object by a surface and acts parallel to the surface in the direction that opposes sliding. Meanwhile, the pulling exerted by a stretched rope or cord on an object attached to it is the so-called tension force. In addition to contact forces, there are also called long-range forces that acts even when bodies are separated by empty spaces. The force between two magnets is an example of a long-range force. As with the force of gravity exerted by the Earth on our bodies, known as our weight. To describe a force vector F, we need to describe the direction in which it acts as well as its magnitude. That is the quantity that describes how much or how hard the force pushes or pulls. The SI unit of the magnitude of force is Newton, abbreviated N. A common instrument for measuring force magnitude is the spring balance. Here's a table of typical force magnitudes of different objects. When you throw a ball, there are at least 2 forces acting on it, the push of your hand and the downward pull of gravity. Experiment shows that when 2 forces F1 and F2 act at the same time at a point A of a body, the effects on the body's motion is the same as if a single force R were acting equal to the vector sum of the original forces. More generally, any number of forces applied at a point on a body have the same effects as a single force equal to the vector sum of the forces. This important principle is called the superposition of forces. The experimental discovery of superposition allows us to replace a force by its component vectors, as we did with displacement previously. Here's a sample problem. Three members of Taylor Swift's fan club are fighting over the last piece of her album Evermore in a music store as seen from above. They apply three horizontal forces to the CD album as shown in the figure. The magnitudes are as follows. We are asked to find the x and y components of the net force on the CD and find the magnitude and direction of the net force. This is just a problem in vector addition. The only new feature is that the vectors now represents forces. To answer the questions and solve the problem, we need to find the x and y components of the net force, so we'll use the component method of vector addition. Once we have the components of r, we can find its magnitude and direction. From the figure, the angles between the three forces are as follows. Consequently, the components of the forces are given by the following equations. Notice that the forces are interpreted or shown in component methods. Upon looking at the components of the forces, we say that the net force has the components R along the x to be negative 100 newtons and R along the y, or the net force along the y, to be 80 newtons. Notice that the net force has a negative x component and a positive y component. This gives us a hint on where the resultant vector lies, in this case in the second quadrant of the Cartesian plane. The next thing that we're going to find out is the magnitude of the net force, which can be taken from the distance formula. So we take the magnitude of the net force to be 128 newtons. For the direction of the net force, we use the relationship of the sines and the cosines to find theta. Now, we take note that there are two possible answers for this one. We have negative 39 degrees and 141 degrees. But since the net force lies in the second quadrant as mentioned earlier, we dare to say that 141 degrees is the direction. For more details and practice problems on the topic, you may view the following references used in this presentation.